Okay, dear student, let us see what is there in this question. Two identical positive charges x and y are placed zero point 0.3 meter apart on a horizontal line. O is a point midway between x and y. The charge on x and the charge on y is positive 4 microcoulomb. Calculate the electric potential at O. So first of all, the diagram is not given as of up to this, but in B there seems to be a diagram which we can utilize for the explanation purposes. No problem. Sketch on the axis the variation of the electric potential V. Okay, no problem. We will be doing that also. Calculate the electric potential at O, and two identical positive charges that are placed zero point 0.3 meter apart. So plus 4 microcoulomb, this is plus 4 microcoulomb, this is also plus 4 microcoulomb, and the total distance is zero point 0.3 meters. That is the total distance between the point x and y. Let me verify that once. 0.3, yes, absolutely correct. So this distance is given as 0.3, and we want to find the potential at O. So how do we do it? First of all, what is potential? Potential due to a point charge, like there is one charge here, okay, and you want to find the potential at this point, which is kind of r distance away. So the formula for that, and this is q, so the formula for that will be kq by r. Point to be noted here, one of the very important point that I'm going to make now: positive charge will be casting positive potential. So potential is a scalar quantity. So technically, if we think like positive potential and negative potential does not make any sense, because there is no direction there. It's not like this is positive and this is negative. But negative charge creates a negative electric field around itself, so that is why we call it negative potential. So if this is a positive charge, the potential will be positive. If it is a negative charge, by the way, so the potential value will be negative. But in this case, because it is positive, we would be taking positive value for the potential, and that will be given by kqr. So clearly we can see that this charge will be creating a positive potential here, plus v1. This is q1, let us say, and because of q2 there will be another potential which is v2. Now we also know that potential is a scalar quantity, which only means that the total potential can be found by just adding them, because like they are scalar quantities, and we need not to worry about the vector summations and all that. Like, there is no other different method of adding it, just simple algebraic method, and we can find the total potential at O. It means that the total potential at O is equal to v1 plus v2. V1 is k, the charge on this, which is 4 micro coulomb, divided by the distance between these two. Now that will be zero point 0.3 divided by 2, which can be taken as 0.15. There will be no square there. Please be very careful. There is no square. Some students are there, those who mistakenly by like they use Coulomb's law here, and they are not able to see the difference between the formula for the force and the potential. So be very careful here. This is potential, so there is no square there. R is raised to power 1 only. So it will be like this, plus the potential due to the second charge. Now the charge, second charge, is also same as that of the first charge. So I can just write it like this. And the distance is also same. So clearly it will be twice of k, 4 microcoulomb, divided by 0.15. Now this will be our full and final answer. So I will not be calculating the answers. We will see the mark scheme and we will see what is the answer that we are getting, but you have the calculator with yourself and you can calculate it. Okay, so let's go to the mark scheme and see what they have done. Okay, so there it is. So the use of kq by r will be the formula for the potential that we will use, and how they have done. This is the value of k, this is the value of q, and this is the value of r. So 240 k volt for one charge is calculated, and because there are two charges and it will be multiplied by 2, so your answer will be 480 kilovolt. And so exactly the same thing is what we have done. So we have done this. Now let us move to next question. Sketch on the axis the variation of electric potential V with the distance between x and y, and we have to say like what kind of potential variation will there be. Okay, let's see. So one thing is clear, that because potential is a scalar quantity, everywhere the final total potential will be sum total of the potential created by both of the charges. So basically we want to comment on what the graph could be for v1 plus v2. So this is a positive charge and this is also positive charge equal. So it will be casting a potential here, let us say V, and even this will be casting a potential, that is V. So this value, it is going to be kind of positive 2V. I'm just taking an example. So positive 2V will be this value. But what happens if we start moving towards some other particle? Like let us say we are going towards this now. Let us say talk about this position. So what will be the potential at this position now, you see? So again, we are only interested in first finding the value of V1 and V2 individually, and then we will add them. So what is the potential V1? So V1 is because of this X, like this is the charge number 1. The distance is increasing. It means that the potential V1 because of the charge X will start, R value is increasing, will start decreasing, because potential formula is KQ divided by R. So potential is inversely proportional to R, which means that if the distance is increased, it moves from O to this point, which is A. Let us say it is moving from O to A. So what happens? The R increases. It means that the voltage will reduce. If the voltage will reduce, it means that the potential because of the charge number 1 is becoming lesser. So V1 is reducing its value, but not that very high, because overall it goes like this exponential behavior. So after some time it will become almost constant, isn't it? But what about the V2? Distance is reducing. For V2, the distance is reducing and it is becoming very, very, very small. So as the distance becomes smaller and it starts reducing its value, the value of the potential becomes very high. So nearer you are, the potential becomes high, and you are literally talking about a point charge. So if this distance becomes tending to zero, the potential because of the second charge will be tending to infinity. It will become very, very high. So V1 is reducing its value but by a very small values, and V2 is increasing its value by a very big gap. It is becoming tending to infinity. So it means that closer you are, the value of the total potential is rising, and it is rising exponentially, so much so that when you are like distance is tending to zero, the value for the total potential will become tending to infinity. There will be an asymptote there. It means that graph should somewhat look like this, like this, like this, like this. So this is the exponential variation, or yeah, I should call it, sorry, not exponential, we should call it hyperbolic, by the way. So V is directly proportional to 1 by R. So it means that if the distance is reducing, this is becoming infinite, and even here it is becoming infinite. It's inverted, it's basically a bowl kind of thing. You can call it, what do they call it? Concave up. Yes, so this is concave up. Let us see what is there in the mark scheme. Are they also saying concave up? Let's see. So symmetric curve around zero with potential always positive. Yes, point number 1, it is symmetric. Point number 2, it is having always positive value. I told you only negative charges can cast negative potential. So both of the charges are positive. There is not even a chance of creating negative potential in the first place. Bowl shape up or curve not touching the horizontal axis. Now that is, this is the third point to be noted. This is the fourth point to be noted, that the minimum value is 2V, but it is not 0. So the minimum value is there and it is also positive. So it goes like this. So this is what is the variation. Clear asymptotes at X and Y, as I have already told you, that the potential is going to become infinite at those very locations. It becomes not defined. So this is how you do it. This is concave up, in the terms of maths AHL, if I'm not wrong. But anyways, okay, let's see what is there in the next question now. Yes. Now, a positive charge Z is released from rest. This is another positive charge, by the way. This was already positive plus Q, and this is also positive charge plus Q. And I'm just assuming it to be small q, and it is released from rest at 0.10 meter from O on the line between X and Y. Okay, so the total distance given was from O to X was 0.15. So he's talking about 0.015. Uh, yes, which is very, very less. Okay. Between X and Y, Z then begins to oscillate about O. Identify the direction of the resultant force that is acting on Z as it oscillates. So, as it oscillates, what could be the value? You see, um, for the resultant force, clearly, this charge is going to create a force because this is also positive, so they will be repelling, and because it is very near to it, so this repulsion will be bigger because the charge is near to X. Now if I talk about Y, so charge is away from Y, so Y will be repelling the positive charge, but that force will be comparatively lesser. So I can only say that it will be like this because the distance of the charge Q, that is at Z, is from Y is much more. So obviously that force is going to be lesser. So overall, this Q is going to experience a force towards right hand side. So it would be moving towards O, no doubt about that. Now let us talk about the other location. Let us say this. Now what is happening here? So because of X, this force will become lesser, but the force due to Y will be much more, and it will be like this. So what will be the resultant force here? Even now the resultant force is looking towards the mean position. So in both of the cases, the restoring force is always pointing towards the mean position. It means wherever the charge goes, either to right or to the left side, in both of the cases the charge is going to come back to the mean position, which only means that yes, it is acting like an oscillation. It is a to and fro motion. It could be simple harmonic, but we would be thinking on that, but it is similar to that. So the oscillation is definitely going to take place, no doubt about that. Now next question: deduce whether the motion of Z is simple harmonic or not. So this answer will be a bit dicey here, because you see that this distance given between X and Y was zero point 0.3 meter, if I'm not wrong, and the half was 0.15. But here you're talking about a very small distance, which is 0.01 meter. So it's kind of 15 times lesser than what the distance was. Deduce whether the motion of Z is simple. Okay, there is another hint. See, usually what happens whenever you are to deduce whether it will be simple harmonic motion or not, you have to find the dependence of force, the restoring force, on the position, on the distance from the mean position. So in this case, that formula for the force is not given. You can be careful here, and you can go to the other paper to questions from the same topic, and you can clearly see that in those cases you would be given a force like the force is approximately equal to 115 into X. So if this kind of a force is given, it clearly says that force is directly proportional to position. This is the hint. Now, if this is given, we can clearly say that yes, it will be simple harmonic motion. But in this case, this expression is not given. So, whenever we create this kind of an expression from ourselves by using the Coulomb's force, by using the Coulomb's law, we will first create a relation in which F will be directly proportional to 1 by x square, or inversely proportional to x square. This variation is not SHM. This variation is not SHM. For SHM, you got to have this variation. Now, this variation is not given. If the distances are very small. If I say that x is tending to 0, then even in this question, we would be using the binomial expansion that you learn in maths AAHL, like x raised to power negative 2 something, and after that we can clearly say that yes, it is converted into simple harmonic motion provided x is equal to tending to 0. So the higher powers of x will be neglected, so only 1 plus nx kind of formation will be there. And it can easily be proved that, see, it will be a simple harmonic motion if the displacement is lesser, but in this question it is not given. Neither they say that the displacement is lesser, and nor they say that the force is equal to this. So if they would be giving you this kind of an expression was given, let us say, then we would be 100% sure it will act like a hint for us that yes, we have to say that clearly force is directly proportional to displacement, and hence it is going to be simple harmonic. But in this case, that is not given, so the answer will be not simple harmonic, and we will say that because the force is actually inversely proportional to the square of the distance rather than being directly proportional to the distance. That is why this is not SHM. Let's see what is there in the mark scheme. Yes. So force is always towards O, and it is always like that. Motion is not SHM because SHM requires the force to be proportional to R, and this force is depends on 1 by R square. So this is exactly the same thing that I have told you to write. So this is how you do it. But there are other questions, like even in IB only, in paper 2, you might find those questions on the YouTube channel already. I have uploaded them, in which the force is given as this. So it can be reduced to this form if we say that x is having a very small value. Then it will become simple harmonic, otherwise not. Okay, dear students, so 7C is over. Is there any other question? No. So this is the end of this question. Okay, so this is Professor Varun. Thanks for joining the YouTube channel. Please tell other students to join the YouTube channel so that even they are benefited with all the services that I'm providing you. Okay, then see you in the next video. All the best. Bye.